All right, it's 4 o'clock. Let's go and get started. All right, good afternoon, everyone. A little bit an hour later than when we usually meet, but hopefully everyone's adjusting to the new time well. How's everyone doing today? Good, doing good. Okay. So the plan for today is we're going to continue on with our lecture notes on inverse dynamics. And so this is the second part of the homework. And so for those of you who have looked at the homework 5 already, this is kind of the second half of that assignment is to basically, come up with expressions to compute joint forces during motion. Okay. And so we'll do a couple of examples of that today. So a couple announcements. Tomorrow, normally I have office hours on Tuesdays from 9 a.m. to 10 a.m. But tomorrow I do have to cancel just because I have to take my father-in-law to the doctor. It's nothing serious. He just needs someone to go with him just because he can't drive himself after what he's going to do. So I'm going to be doing that. I'm gonna try to see if I can make up the office hour times later in the week. Maybe Thursday morning. I think that's probably what I'm thinking. So maybe I'll do Thursday 9 to 10, and then that's in addition to the normal Thursday hours from 1 to 2. But I need to see how my schedule is going to shake out the next couple of days. Okay. All right. So the other announcement I want to make is that I want you guys to really start to kind of talk to each other and form groups and pick topics for your final project. And I'm going to set a deadline for it. So I'm going to set a deadline of this Friday. Okay. So I'm going to send an email out today, right when I get back to my office, just to confirm this. So a few groups have already kind of reached out to me. So some topics are already starting to be taken up. But the most important thing is that before we kind of get into next week, before we get into week 13, I want everyone to be in a group, and I want everyone to know kind of what they're researching, because you're most likely probably going to use the Thanksgiving break to at least do a bit of the research, and then after Thanksgiving we have just that 1 week of lectures, and then right after that it's final presentations. And so you guys really need to know kind of who's in your group so that so you can kind of get started working on this. Okay. Okay, but I'll send an email to confirm that. So if you have not chosen a topic yet, or if you're not in a group, definitely start getting on top of that. And if you're having trouble finding a group, I've had a few people reach out to me and said that I have one person with me, or I have two persons with me, and then if you're a single person, or if you're a pair trying to look for a group, let me know, and then I can kind of pair you up with some of the groups that have formed already. Okay. But I want everyone to form their groups. I want everyone to pick their topics by this Friday. Okay. And again, if you have a group of people, but you are kind of struggling to find a topic, then let me know as well. I can definitely help you guys with choosing topics for the project. Okay. Okay. So that's all my announcements. Are there any questions I can answer before we get started for today? Okay. All right, everyone on Zoom, can you guys hear me okay? Okay, good. Okay. All right, so let's go and get started. And we're just going to pick up where we left off last time. So we're talking about inverse dynamics. Okay. So we are kind of smack dab in the middle of our human dynamics section, right? And so, the whole point of this section is to analyze human motion. And to ultimately, what we want to do is we want to compute the muscle forces and joint reaction forces that occur during human motion. Okay. Okay. And so in that sense, our goal here really isn't all that different from the first unit of this class, which is human statics, right? It's just that when you get motion involved, things just naturally become a lot more complicated because first of all, the body parts are moving, and second of all, you have to consider not only the static forces but also just the additional forces that come from like acceleration and dynamic forces. Okay. And so to accomplish this, there's kind of a three-step process that we've been, kind of subtly working through kind of this whole time. And so the first one is human motion kinematics. Okay. This one we've completed already, and so this is a nice kind of green check mark there. Okay. And so remember, the goal with human motion kinematics is to obtain measurements in a systematic and kind of consistent way of the joint angles and the motion of the human body. Okay. And remember, this is typically done through motion capture. Okay. So that's done. We've already kind of finished covering that, or at least to the extent that we can in this class. Okay. All right. So we're currently on step 2. So inverse dynamics, and so let me put an orange. We'll call this in progress. Okay. Okay. And so the idea with inverse dynamics is to take the kinematics, take the measurements of the joint angles, and convert those into net forces on the body segments. Okay. So today we're going to do a couple of examples to kind of show you kind of what that process looks like. Okay. And the thing with inverse dynamics, and you know, this is kind of true all through for all steps in this process, that you know we can do relatively simple examples in the class, mostly 2D examples. But when you start to get into actual practical data, you know, for the most part, that data, just with the amount of equations and variables involved, is a little bit too complex to kind of handle by hand. And so what we're going to focus on mostly in the class is mostly just kind of setting up the equations and kind of the logic behind that. And then I'll show you a little bit of MATLAB code that you can use to actually compute these things. Okay, but the coding is not going to be a focus in the class. The focus of the class is kind of more how do you set up the equations and kind of the logic behind that. Okay, and that's especially true for the last step in this process, because what we're going to get from inverse dynamics is we're not going to get quite there yet. We'd be able to compute individual muscle forces. What inverse dynamics is going to give us is kind of more of a net force on a body segment. Okay, and so to convert that net force into individual muscle forces, you need to run an additional step of the process called muscle force optimization. So this is kind of the next step. And so this is what we're going to cover probably starting Wednesday, and going into the next week and after Thanksgiving as well. Okay. Okay. All right. So that's kind of the 3-step process, and traditionally, in kind of a more kind of I said biomechanics setup that you might have in a lab, all 3 of these processes would probably be handled by the same code. Okay. And so basically the way it would work is that, you'd have your subject kind of, put on the mocap suit, put on the mocap markers, go through the motion. And then in real time or semi-real time, you have a computer that's kind of processing this data, doing all these calculations with the equations and giving you the muscle forces kind of as a result. Okay. Okay. So that's kind of just the overview of the whole process, because I don't think we've talked about kind of where we're going with all this information yet. So I wanted to kind of start today with that. Okay. But of course, we're not all the way there yet. We're stuck on inverse dynamics here. Okay. And the whole idea with inverse dynamics is to basically apply what you know about kind of traditional dynamics to human body motion. Okay. And so essentially what we're doing is we're writing out the equations of motion for each body segment, and then plugging in our data from the kinematic section from external forces and whatnot. Okay. Okay. And so what you're going to see is that for each body segment that we have in our motion, or each body segment that we're considering, we're going to have a sum of the forces in the x direction. Okay. That's going to be equal to the mass times the acceleration in the x direction. Sum of the forces in the y direction is going to be equal to m(a)y, which is the mass times the acceleration in the y direction. Okay. And the sum of the moments is going to be equal to the moment of inertia multiplied by the angular acceleration plus rp cross product with m(a) vector. Okay. Okay, so at the end of class last Wednesday, we talked about what that last term in the moment equation is. That term is basically just there to kind of compensate if you're summing up the forces in a location other than the center of mass. Okay, because that moment of inertia I there is computed, relative to that center of mass. And I think one thing that I didn't mention last time is that these accelerations, they do have a particular meaning. So, or I should say we should be a little bit more specific what we mean by these accelerations. And of course, that goes for this one as well. Okay. And so these accelerations, these are basically the accelerations of the center of mass of the body segment in question. Okay. And then what you'll see too is that this center of mass, we can write this acceleration in terms of the human motion kinematics that we would get from motion capture. Okay. Okay. And remember, from the human motion kinematics, we mostly obtain kind of the angular kinematics of the motion. So things like angular position, angular velocity, and angular acceleration. Okay. So this would be in terms of theta, omega, and alpha. Okay. You'll see what I mean once we kind of get into the examples, right? So basically, once we get into the examples, we're going to replace those acceleration components by expressions that have the angular velocity, angular acceleration, and some corresponding geometrical qualities. Okay. Okay. So that was just a summary, kind of just an overview of kind of the process as we know it. Okay. Any questions on this before we jump into an example? Okay. All right. So let's do our first example. Okay, so in this example, we're gonna analyze the inverse dynamics of a person doing a squat. Okay. So I think everyone's kind of seen a squat before, although you probably have not seen one like this with my terrible drawing. But you're gonna have to use your imagination a little bit. Okay. So we're just focusing on the lower body in this case. And so, so this one right here, this first segment, this is the lower leg. So this is the shank. Okay. This next segment right here, this is going to be our thigh. And then, because the upper body doesn't really do all that much during a squat, it's mostly just there to maintain balance. We're going to basically lump it all together. And so this third segment here is basically kind of a lumped mass representation of the entire upper body. Okay, so that includes your torso, your arms, your head, your neck, your back. Okay, those aren't that relevant during a squat, so we're just going to lump it all together. Okay. And of course, this triangular thing at the bottom that's attached to the ground, this is our foot. Okay. All right. So those are the body segments that we're considering. The foot technically is not a body segment because we're going to assume it's fixed to the ground, but it's still there. Okay. But most importantly, we have three joints in this figure. So we have the ankle joint that joins the foot together with the shank. Okay. The joint in between the shank and the thigh, of course, is the knee. Okay. And then the joint in between the thigh and what we're calling the upper body, that is the hip joint. Okay, and so we're going to focus primarily on the joints in this analysis here. Okay. Okay, so let's go ahead and label some properties on here. And so this first example here, we're just going to do everything in terms of symbols. So there are no numbers here, but we have to kind of know kind of what our symbols are and what they represent. Okay. All right, first let's go ahead and draw in the kinematics. And so we're going to assume that we have all of the joint angles and their change with time. Okay. And so for our three body segments here, we're going to have three angles to worry about primarily. And so the angle that the shank makes with the horizontal, we'll call that theta 1. The angle that the thigh makes with the horizontal, we'll call that theta 2. And then the angle that the upper body makes at the hip, we'll call that theta 3. Okay. And notice the way that I've drawn all these angles. These are angles with respect to the horizontal x-axis. Okay. All right. So next thing I'm going to identify in each of these body segments is the center of mass, as well as its moment of inertia. Okay. Okay. So for the shank, the mass of the shank is going to be called M1, and its corresponding moment of inertia taken with respect to that center of mass is going to be I1. Same thing for the thigh, and so we're going to assume that the thigh has center of mass M2, and its moment of inertia is I2. Okay. And then for the upper body, we're going to assume that it's a gigantic lumped mass, and so we're going to assume that it has a mass of M3, and its corresponding moment of inertia is I3. Okay. So all of these we're going to assume is given, just because these are all kind of relatively easy to measure or compute. Okay, so next thing we're going to need is we're going to need some geometric measurements, and so we need the lengths of each of these body segments. Okay. So we're going to assume that the shank has a length of L1. Okay. We're also going to pinpoint the location of the center of mass. Okay, so because we're not going to assume that it's just in the middle, and so we're going to assume that the location of the center of mass relative to the ankle joint for the shank is given by a variable called R1. Okay, so L1 is the total length of the body segment. R1 is just the distance from the joint to the center of mass. Okay, and we're going to have those same measurements for each of the other body segments here. Okay. So the total length of the thigh segment is going to be L2. Similarly, we have the distance between the knee joint and the center of mass of the thigh. That's R2. Okay. And then for the upper body, we just have one length here. So that's going to be the length from the hip joint to where the lumped mass is. So we'll call that one L3. All right, last thing. And so, there's a lot going on in this figure. So, I wanted to kind of take time to kind of go through each of it. We're going to assume that we know. So we're going to assume that this person is standing on a force plate underneath it. And so we will be able to obtain the normal force that the ground is exerting onto the foot. Okay. And we're going to assume that this has a magnitude of F of G and is pointed straight upwards. Okay. All right. So a lot going on in this figure, but we're gonna use basically all this information. So none of this is extra information. Okay. So with that given, let's go ahead and state out the objective of the problem. And so in this problem, we want to compute the net forces and net moment at each of the joints. Okay. And so we have three joints in this figure here. So we have the ankle joint, the knee joint, and the hip joint. Okay. And so we're going to have expressions for the net forces and net moments at each of these places. Okay. All right. So that's the setup for the problem. Any questions with the setup or the geometry here, or the location of any of the variables? Okay. All right. So the way we're going to do this is we're going to be drawing free body diagrams. Anytime you have a problem that asks for forces or moments, there's kind of no way around it. So you have to compute free body. You have to draw free body diagrams. And so we're going to do those for each of the body segments. So starting at the foot, that's going to give us the equations for the ankle. Then we're going to do the same thing for the shank and the same thing for the thigh. Okay. What's interesting for this problem is that the upper body is not actually going to factor into our calculations, and we'll talk about that more kind of after the example. Okay. Okay. So let's start with the free body diagram of the foot. Okay, so the foot is actually stationary in this case, but the reason we're starting with the foot is because that's where the external force is being applied. Okay, and so the thing about these inverse dynamics problems is that you have to have for the most part you need to have some kind of external force acting on your system. Okay, and wherever that external force is being applied, that's usually where you should start. Okay, and kind of that terminology will make a bit more sense after this. Because whenever you're doing these inverse dynamics problems, there's usually multiple different places where you can start your analysis. Generally, you want to start the analysis from the place where the external force is being applied. Okay. Okay. And so for this particular problem, we have the added bonus that the foot is stationary, and so that helps us out quite a bit. But that's not always going to be the case. Okay. It just so happens that our starting point here is also a stationary body segment, but that's not always true. So don't always assume that when you're doing these problems. Okay, so let me go ahead and draw our foot. Okay. Our little triangular foot here. Okay. Okay, so up here, what I have is this is the ankle joint. Okay. We're going to assume let's assume that our normal force is being applied at the toe. Okay. And we're going to be as general as possible. So let's go ahead and add both components, the x and y components of the normal force. Okay. Even though for the most part, if you're going to be doing a squat, most of the force is going to be vertical. But you might still have a horizontal force that's mostly just there for balance. Okay. So let's do this as 2. So let's assume that we know the geometric dimensions here. And so we're going to assume that your foot has a height of h. And the horizontal distance between your toe and your ankle is going to be given by L. Okay. The reason I'm including those is because at your ankle joint, we're going to have some internal forces. Okay. And so basically, in order to satisfy the equations of motion here, we need to add some additional forces so that things are going to balance and cancel out. Okay. Okay, so first thing we're going to do is we're going to have a net force in the y direction, Fy1, and net force in the x direction, Fx1. Those are going to be applied directly at the ankle joint. Okay. And then we're also going to have a net torque or net moment at the ankle joint, which we'll call T1. Okay. So these forces here, so Fx1, Fy1, and T1 are net internal okay. So these are net internal forces that are acting at the ankle. Okay. And so, anytime you have motion, you're going to have these net forces at your joints. Okay. And so we're just kind of giving them a name. Okay. And so for this particular part of the problem, those internal forces, these are the unknowns that we can solve for. Okay. And the way we're going to do these is by writing out the equations for the equations of motion. Okay. And so conveniently, we have three equations of motion. We have Fx, Fy, and the sum of the moments. Okay. And so that's going to be perfect for us for solving for these forces here. Okay. Okay, so let's go ahead and do that. So we have some of the forces in the x direction. Okay, and so we have two forces in the x direction here. So we have Fgx, which is the normal force from the ground, as well as Fx1, which is the horizontal force at the ankle joint. Okay, so we have Fgx. Okay, so we give that a positive sign because that force is pointing in the right to the right. Okay, and then from that we're going to subtract Fx1, which is the net force at the ankle joint. Okay. And this is going to be equal to the mass of the foot multiplied by the acceleration of the foot. Okay. But we already know that the foot is stationary. Okay. And so if the foot is stationary, that means its acceleration is also 0. And so this is going to be 0 here. Okay. Okay, so let's do the same in the y direction. And so we're going to have the same equations here. So we have Fgy minus Fx1, or excuse me, Fy1. Okay. This is going to be equal to the mass of the foot times the y acceleration of the foot. Okay. But because it's stationary, that's going to go away and go to 0. Okay, and then finally, we're going to sum the moments around the ankle joint. So this is kind of traditionally how we did it in our statics unit, right? And so to kind of reduce the number of terms in our moment equation, you can sum the forces around the joint itself. Okay. And so if we're summing the moments around the joint, then Fx1, Fy1 are not going to enter into the equations. Okay. But we are going to have contributions from the normal force. And so we're going to have Fgx, okay, multiplied by its moment arm, which is h. This is a counterclockwise moment, and so we're going to give it a positive sign. Okay. Then we're going to subtract Fgy times L. Okay. And so that's the contribution to the moment from the y component of the normal force. Okay. We give that a negative sign because that contribution is clockwise. Okay. Okay. From that, we subtract the net torque at the joint. So that's going to be a minus T1. Okay. Okay. And all that is equal to, the moment of inertia times the angular acceleration plus that extra term. Okay. But again, this is all stationary, and so all this is going to be 0. Okay, so these are our 3 equations here. For this particular body segment, the equations ended up pretty simple. So we can solve these very easily. Okay. Okay. And so if we solve these 3 equations, we get fx1 is equal to fgx. Okay. Fy1 is equal to fgy. Okay. And then T1 is equal to fgx times h minus fgy times L. All right. So fairly straightforward. In fact, this is basically just like our statics problems because we don't have any acceleration. Okay, at least not for the foot. But what we're going to see is that in the next part of the example, we're going to do a free body diagram of the shank. Okay, and so from that, because the shank will be moving throughout the squatting, action, these expressions here are going to change quite a bit. Okay, but this is kind of a good warm up, kind of a good reminder of us, kind of how do we form our equations. Okay, any questions on this part here? Okay. Okay, so let's go ahead and move on to the next segment. Okay. So the next segment is the shank. And so just like the ankle or just like the foot, we're going to draw the free body diagram of the shank. Okay. Okay. So our shank, at least the way it's shown in the figure, looks something like this. Okay. First off, we have its center of mass here. Okay. I'm drawing it as if it's in the center, but it doesn't have to be completely in the center, right? Remember, we have separate variables to describe kind of the location of the center of mass. Okay. And so this is going to have M1, I1. Okay. Of course, this is going to have its own gravity force. And so we have M1G. Okay. All right, so we have the geometric quantities here. So we have the distance between the ankle joint and the center of mass. We call that R1. Okay. And then we have the total length of the shank segment. We'll call that L1. Okay. All right. So since the shank segment is going to be in motion, we are going to have knowledge about its kinematics. Okay, and so of course the kinematics that's given directly in the figure is θ1. Okay, so θ1 of course is going to be known. Okay. But remember, if you know θ1, that means you know all of its derivative as well. So that means omega one being the angular velocity, and alpha 1 being the angular acceleration of this joint, also are known. And so we're going to see how those quantities factor into our calculations here. Okay. So the last thing that we need here is going to be the reaction forces at the joints. Okay. So we actually have two joints here, right? And so this is a little bit different than our ankle joint where we had just or different than our foot where we only had the ankle joint to worry about. Okay. Here we have a joint on the bottom of our segment as well as on the top. Okay. So on the bottom here we have our ankle segment. Okay. And so that's going to be fx1, fy1, as well as the torque there, or the moment, we'll call it T1. Okay. And then we have corresponding quantities at the top. So we have Fy2. Okay. So these are going to be the joint reaction or the net joint forces and the net joint moment at the knee. Okay, so that's going to be Fy2, Fx2, and T2. Okay. Okay. And so just like in the previous step here, we're going to compute expressions for all the joint reactions. Okay. The good news is that because we started from the foot, we already have expressions for all of these here on the bottom. Okay? And so these are already known. From the previous part. Okay. And so when we write out our equations of motions for the shank, we're going to use these variables as if we know them. Okay. Because we do. Okay. And so the three unknowns in this part are going to be the net joint forces and the net joint moment at the new joint that we haven't considered yet, which is the knee. Okay, so that's Fy2, Fx2, and T2. Okay. So there's one kind of subtle thing here that I want you guys to kind of take note of. Okay. And so the joint forces at the ankle, we had already computed those from the last segment. Okay. And so, the reason they're appearing here as well is because, anytime you have a force that's acting at a joint, okay, by Newton's third law, we know that, that force is being applied equal and opposite to whatever it's in contact with, right? And so because our foot is directly connected to our shank through our ankle, right, any force that that is experienced at the ankle is going to affect our foot and our shank equally, right? So equal magnitude, but the directions are opposite. Okay. And so if you look at the directions of the arrows at the shank joint here, or excuse me, at the ankle joint that I drew, and if you compare that to the directions of the arrows that we drew in the free body diagram for the foot, okay. So both the things that I've circled here in pink, those are the exact same forces. But if you look at the directions that I chose, the directions are opposite. Okay. Right. So Fx down here on the shank is going to the right. For the foot, Fx is going to the left. Okay. Fy on the foot is going down. Fy on the shank is going up. Okay. T1 on the shank is going counterclockwise, whereas T1 on the foot is going clockwise. Okay. So these have the same magnitude. Same magnitude as the previous segment, just opposite directions. Okay. So that point's really important there because, just because of the way the human body is connected, right? You're going to have, multiple segments make use of the same joint forces. Okay. And so, it doesn't really matter exactly what direction you choose for the forces when you're first introducing them, but just know that when you're bringing those forces back on the next segment, you want to use their opposite directions. Okay, otherwise you're not going to have a consistent system. Okay. All right. Any questions? Any questions on this? Okay. All right. So that's the first thing. First thing that's different here. Okay. The next thing that's different here is that this center of mass, right, the shank, is not going to be stationary. Okay. And so as the body kind of goes through its motion, the position of the center of mass is going to move. Okay. And so we need to account for that in our equations of motion. Okay. Okay. In particular, the way that we account for it is that we have to come up with expressions for ax and ay. Okay. Ax being the linear acceleration of the center of mass for this shank segment, and ay being the linear acceleration in the y direction for this shank segment. Okay. And so the way we're going to compute these is we're going to take derivatives, right? And so we're going to take the second order derivative of x of t, okay, which is the horizontal position or the x position of the center of mass of the shank. And then ay is going to be the second order derivative with respect to time of the vertical position of the shank. Okay. So let's do these one at a time because they involve some derivatives. Okay, so let's come up with an expression for the horizontal position of the center of mass. Okay, and remember, by center of mass, in particular, I'm considering kind of this little ball right there, right? So that's kind of exactly where we're measuring M1 and I1. Okay, and so to get the horizontal position of the center of mass, we're just going to use trigonometry here. Okay, and so we know the distance. The distance from the ankle joint up to the center of mass is given by R1, okay? And we know the angle that the shank is making with the horizontal at that time, which is theta 1, okay? And so the horizontal position of this mass, M1, is going to be simply R1 cosine theta 1, okay? Well, remember, theta 1 is going to change with time. So it's going to be R1 cosine theta 1 of t. Okay, so first thing we're going to do is we're going to take the first derivative, okay? And so we're going to take dx dt, which is going to give us vx t. Okay. So let's go ahead and take this derivative. And so we need to do a little bit of chain rule, okay? So R1 is going to be constant, right? So we're going to assume that, we're not, Mrs. Incredible or something where we can stretch our limbs, right? So our limbs are going to be for the most part, a fixed length, right? So R1 is just going to kind of be along for the ride. Okay? All right, next we have the derivative of cosine of theta 1 of t, okay? And so we have kind of an inner derivative that we need to take into account, right? And so the inner derivative is going to be the time derivative of theta 1 of t, okay? And so that's going to be omega 1, okay? So this omega 1 comes out due to chain rule, okay? Chain rule of the inner part. And then the other part that's going to come out is the derivative of the outer function, which is cosine of the theta, right? So derivative of cosine is minus sine. Okay? So it says minus sine of theta 1 of t. Okay. kind of just make a little bit more room here. Okay. Okay, so of course you can simplify that, so you can bring the negative out in front. And so the velocity of the center of mass here is a minus R1 omega 1 sine of theta 1 of t. Okay, so when you're taking derivatives of these expressions here, don't forget the chain rule, because otherwise you're not going to get the right expression. Okay, and omega 1 is perfect, actually, right? Remember what we said about our human motion kinematics. We should know kind of the angle that the ankle joint is making. We also know its angular velocity and its angular acceleration too, right? So everything here on the right side is known. Okay. So everything here is known. All right, but we're not done just yet. And so what we want is, we don't necessarily want velocity. Sometimes we do, but what we need to plug into our equations of motion is the acceleration. Okay? And so to get acceleration, we need to take one more derivative. Okay? So we're going to take the derivative of Vx with respect to time. Okay, and so that's going to give us Ax. And here, unfortunately, we have to use not only chain rule, but product rule as well, okay? Because if we look at our expression for the velocity, we have two quantities there that depend on time. We have omega 1, okay? Omega 1 is going to change with time, as well as theta 1, right? So theta 1 is also going to change with time as well, okay? Okay, so let's go ahead and take one more derivative. And so through the product rule, I'm going to take the derivative of omega 1 first. Okay? And so the derivative of omega 1, the derivative of angular velocity is going to be angular acceleration. So that's going to be minus R1 alpha 1. Okay. Sine of theta 1. Okay. Minus. Then we're going to take the derivative of the second part of the product, which is the sine theta 1t, which we again need to use our chain rule for. Okay. So this can be an R1 minus R1 omega 1 squared. Okay. Because we have the original omega 1 that was there before, and then we have another omega 1 that comes out of the chain rule of taking the derivative of sine of theta t. Okay. And then we have the derivative of sine of theta t, which is just a cosine theta 1 of t. Okay. The t is there. I just just in the interest of space, I neglected it. Okay. And so this is the expression that we have for the linear acceleration for the center of mass for the shank. Okay. And so we're going to plug this into our force balance. Okay. Any questions on how we obtain this this result here for the acceleration? Okay. All right. So let's do the same thing for AY. This one I'm going to go a little bit faster just for the sake of time. Okay. Okay. So first we're gonna write out our expression for y of t. So y of t is going to be an R1 sine of theta 1. Okay. The y of t. This is just going to be the derivative of this with respect to time. And so just like before, we're gonna take our chain rule. So we have R1 omega 1 cosine theta 1. Okay. And then AY of t here is we're going to take one more derivative of this, which is R1 alpha 1 cosine theta 1 minus R1 omega 1 squared sine of theta 1. Okay. Okay. So now that we have expressions for the linear acceleration of the shank, we can go ahead and plug this into our equations of motion. Okay. first, let's sum the forces in the x direction. Okay. So it feels like it's been like 30 minutes since we looked at the three-body diagram. So let's kind of remind ourselves. Okay. And so the x direction here, we only have two forces, and so we just have the net joint force from the ankle, which is Fx1, and the net joint force from the knee joint, which is Fx2. Okay. Okay, so the sum of the forces, this is actually the simplest part of the problem. So we're going to have an Fx1 minus Fx2. Okay. This is equal to M1 times AX1. Okay. So the mass times the horizontal acceleration of the shank. We just solved for our expression for the acceleration, so let's go ahead and plug that in. And so this can be M1 multiplied by minus R1 alpha 1 sine theta 1 minus R1 omega 1 squared cosine of theta 1. Okay. Okay. Okay, so let's do the same thing in the y direction. Okay. And so in the y direction, we're going to have one more force here. So not only do we have the forces from the two joints, okay, so we have Fy1 minus Fy2. We also have gravity, so we have M1G. Okay. This is equal to the mass M1 multiplied by the vertical acceleration, which is the expression that we got just above there. So I'm just going to plug that in. Okay. So it's M1 times R1 alpha 1 cosine of theta 1 minus R1 omega 1 squared sine of theta 1. Okay. So far, so good. So the last equation that we have here is the moment equation. Okay. Here we're going to change things up a little bit, right? And so you know, you have a couple of options here with the moment term, right? And so with the moment, you know, traditionally what we usually do is we sum up the moments around one of the joints, right? And so we pick, you know, in this case we could either pick the ankle joint or we could pick the or the knee joint, right? And remember, the reason we did that was so that, you know, we could avoid writing those joint forces into our moment equation. You could still certainly do that, and so that's definitely a valid path to go. But another path that we can go is we can sum up the moments instead around the center of mass. Okay. The reason we want to do this is that, you know, if you recall back from our moment equation, right, we have that additional term that that's there to kind of account for you know, the motion of the center of mass, right? And so, you know, I'm just going to write it here just to kind of remind you, right? So if we don't, sum around the center of mass, we have this extra term. And so this extra term was RP cross product with M acceleration vector. Okay, where that RP vector is that's the vector that points from the wherever the center of mass is to wherever you are summing the moments around. Okay, and of course M is the mass, and the acceleration vector is these two components of acceleration that we just found. Okay. All right. And so you can certainly do this if you're a fan of cross products and you're a fan of doing cross products with symbolic you know, algebra like this. That's, you know, you're definitely more than welcome to do that. You're still going to get the same answer, It's just for me and my own sanity. I prefer not to do cross products with symbols if I can. So, and so to do that, we're going to sum the moments around the center of mass. That means we're going to have a few more terms than what we normally have, just because we're none of the joint reaction forces are going to cancel. But I think it saves us from doing this cross product, which I think is pretty worth it. Okay. Okay. So with that said, let's go ahead and sum the moments. Let's start with the raw torques, the raw moments. And so we have T1 counterclockwise, so it's positive, minus T2. Okay. I'm going to go ahead and erase this node because we're going to need to go down here. Okay. Okay. So remember this T1, T2 here, these are the raw net moments at the ankle and knee joint. Okay. And so even though they're acting at two different places, when you're summing up the moment equation, you can just add them together just like that. Okay. With their appropriate sign, of course. Okay. So if one is clockwise, you put a negative and so on and so forth. Okay. Now we have the contributions to the moment from all of the joint forces. Okay, so first we have the contributions from the ankle joint, right? So this is Fx1 multiplied by R1, okay, sine theta 1. Okay. Minus Fy1 R1 cosine theta 1. Okay. So what I've done here is I've broken up, those forces into their components, and I'm multiplying them by their respective moment arms relative to the center of mass, which is where we're multiplying it from. Okay. Plus, I need to erase this just so it can come down here. Okay. So those are the contributions from the ankle joint. Now we have the contributions from the knee joint. Okay. So we have plus Fx2 multiplied by L1 minus R1. Okay. So remember, the knee joint is on the other side of the segment relative to the ankle joint. So we don't have that exact measurement of the distance between the knee joint and the center of mass. And so we need to take the difference of L1 minus R1. Okay. L1 minus R1 quantity multiplied by sine theta 1. Okay. And then likewise, we have a minus Fy2 times L1 minus R1. Oops. Cosine theta 1. Okay. And this is all equal to the moment of inertia multiplied by the angular acceleration of the shank, alpha 1. All right. And so the right-hand side of this equation is much simpler because we took that moment, we summed the moments around that center of mass. Okay. All right, and so these are our equations of motion. And so let me just remind you kind of what which ones the unknowns are. So we have Fx2, Fy2, T2, okay? And we have a couple more Fx2s and Fy2s as well, okay? So everything that I've circled in pink there, those are the unknowns. And so the next step of this process is to solve these equations for those unknowns there. Okay. Everything else that I haven't circled is known already, either from the kinematics part of the problem, or they were solved for in the previous free body diagram. Okay. All right. Any questions on this? Okay. All right. So let's complete this step. So let's go ahead and solve for these circled quantities. Okay. And so, of course, I'm skipping the algebra mostly here, but it's mostly just kind of algebraic manipulation. So just adding stuff. For the most part, you're just kind of moving terms around just by adding and subtracting. So, definitely verify this. And so definitely go through your notes and verify that this is the case. But just for the sake of time, I'm just going to skip to the answer. Okay. Okay. So for fx2, we have fx2 is equal to fx1 plus m1 times quantity r1 alpha 1 sine theta 1 plus r1 omega 1 squared cosine theta 1. Okay. Probably the shortest expression that we have. Okay. Fy2 is Fy1 minus M1G minus M1 R1 alpha 1 cosine theta 1 minus R1 omega 1 squared sine of theta 1. Okay. Okay. And now we have T2. Okay. Of course, T2 is going to depend on the results for fx2, fy2. I'm not going to plug those in because otherwise this can be a four-line expression here. But just know that you do have to plug those in. Okay. Okay. So for T2, we have T1 minus I alpha 1 plus fx1 r1 sine of theta 1 minus fy1 r1 cosine of theta 1, okay, plus fx2 times L1 minus R1 sine of theta 1 minus Fy2 L1 minus R1 cosine theta 1. Okay. All right, and just know that this quantity fx2 and fy2 you would plug in for these here. Okay. And so if you wanted to write out the full expression, then that's kind of what you do. Okay. But usually, for the homeworks and for the exams, of course, this is kind of this is an adequate place to stop. Okay. It's already kind of a very long expression. All right. Any questions on how we obtain these results here? Okay. All right. So we have 10 more minutes. I'm looking and see how dark it's getting out there. It's depressing. Okay. So of course, we're not done with the problem just yet. We have one more body segment to go through, but it's going to be kind of more of the same stuff. Okay. So I think what I'll do is I'll start it. Let's go ahead and write out our expressions for ax2, ay2, and then we'll kind of finish it all up next time. Okay. I do have one more example that, of course, we'll do next time as well. And the next example actually has some numbers to it, so I think that'll help with it. Okay. Okay. All right. And so the last segment that we're going to go over is the thigh segment. Okay. And so ultimately what this is going to do is it's going to give us the net joint forces and the net joint moment at the hip joint. Okay. Because so far we have expressions for the ankle joint and the knee joint, and then we're just kind of working our way up to the last joint. Okay. So let's start with the free body diagram. Okay, so for the thigh segment, it looks quite similar. Okay. Okay. All right, so the angle that the thigh segment makes with the horizontal is theta 2. We have its center of mass. M2 and its moment of inertia I2. Okay. We have its gravity force, and so the gravity force we'll call M2G. Okay. We have its geometric dimensions, and so the distance between the knee joint And the center of mass, we're going to call that R2. And the entire length of the segment, we'll call it L2. Okay. All right. And then the last things that we'll need to note here are the net joint forces. Okay, so we have the forces at the knee joint first. And remember, we're going to draw these in the opposite direction of what we drew in the previous free body diagram. Okay, so this is Fx2, Fy2. And then we also have the net moment, T2. Okay. So remember, these three quantities in purple here, we just solved for them. But, they're equal, they're equal and opposite counterparts are acting on the thigh joint rather than the thigh segment relative to the shank. Okay, and then finally we also have the net joint forces and the net joint moment at the hip as well. Okay, and so this is going to be Fy3, Fx3, as well as T3. Okay, so everything up here is the net at the hip. Okay, whereas down here is the knee. Okay. All right, so the thigh is a segment that connects your knee and your hip. Okay, so we're going to go through the same process here, and so it's just kind of just rinse and repeat. Okay, and so that's kind of the nice thing about inverse dynamics, is that it's you're kind of following the same process over and over again. It's just kind of a very long and kind of tedious process. Okay. So before we go, let's go ahead and write out the expressions for AX2 and AY2. Okay. Okay. So that's the linear acceleration of the thigh center of mass, M2. Okay. And so just like we did with the shank, we're going to start with the horizontal position, x of t. Okay, so we'll call this x2 of t. And then we're going to take its derivatives in order to get, vx2 and then ax2. Okay. Okay. And so let's start with the horizontal position here. And so first thing, just based on this geometry here, we have R2 cosine of theta 2. Okay. But we can't just leave it at that for here. Okay. Because if you recall kind of from the past section, right, the knee joint is actually mobile, right? And so as this person kind of goes through their squatting motion, the knee is not going to be in the same place as it was, second to second, right? That was different from our last segment, because if you remember our last segment, we were measuring the position of the shank relative to the ankle. But the ankle was actually fixed with time, because the foot was not changing its position. And so we need to account for the fact that the knee's position is going to change with time as well. Okay. And so to this, right? So this part right here, this R2 cosine theta 2, this is the position of thigh center of mass relative to the knee. Okay. That's kind of exactly as we've kind of drawn it in the figure there. Okay. To that, we need to add the position of the knee joint relative to a fixed point on the model, which in our case conveniently is going to be the ankle joint. Okay. And so this is going to be plus L1 cosine theta 1. So this right here is the position of the knee joint relative to the fixed angle. Or I guess I should say the stationary. Okay. Okay, and so that kind of doubles our work here. So we're going to have more derivatives to take into account. Okay, does that kind of make sense of why we need two terms for this position here? Okay, so let's kind of very quickly kind of take its derivatives. And so let's take the first derivative, and so that's going to be v2x of t. Okay, so we're going to take derivatives with respect to t. Remember that we need to use our chain rule. So we have a minus r2 omega 2 sine of theta 2 minus L1 omega 1 sine of theta 1. Be careful with your subscripts here because it's very easy to kind of get confused. Okay? And in fact, I already made a mistake. This first term should be minus r2 omega 2 sine of theta 2. Not sure why it's not letting me erase this. Probably because my stylus is not on. Okay. Theta 2. There we go. All right, so be careful with the subscripts. And so it kind of gets very tempting to kind of fall into a rhythm. And if you fall into a rhythm, then you can kind of make some mistakes like that. Okay. So let's take one more derivative here. And so that's going to give us the acceleration. Okay. And so we're going to need a product rule both of these terms here. And so we're going to have a minus R2 alpha 2 sine of theta 2. Okay. Minus R2 omega 2 squared cosine of theta 2. Okay. Minus L1 alpha 1 sine of theta 1 minus L1 omega 1 squared cosine theta 1. All right, so this is just the acceleration. So we need to plug this into the equation of motion, and we're gonna have the same kind of a similar thing for y, and then that's gonna make our moment equation even more, even more crazy. Okay. So very quickly, you can see here that the more segments that you add, these expressions kind of get crazy. So for these sections, for this kind of section of the course here, remember, like I mentioned today, we're gonna focus more on kind of setting up these equations more so than actually plugging in the numbers. Although in the next lecture, you'll see what plugging in the numbers actually looks like. Okay. All right. Any questions on this before we wrap it up for today? Okay. All right. So that's all we got time for today. So thank you guys for coming. Remember, office hours tomorrow is canceled, but I'm probably going to make up those office hours on Thursday morning. So keep an eye out for that. And if you haven't chosen your groups yet, you haven't chosen your topics, make sure you guys are working on that as well. Okay, because I want you guys to choose your topics and groups by Friday. All right, so thank you guys. I hope you guys have a good rest of your evening. Be careful getting home. It's very dark right now, much darker than it is normally. And I will see you guys next on Wednesday. Oh yeah, so midterm exam is next Wednesday, and so we'll go over the study guide for that on next class on Wednesday. Yeah. Thanks, guys. Yes.
Professor, do you have a minute to talk about the project?
Sure. What's up?
Okay, so basically, we have picked some topic.
Okay.
Like, we're gonna do us three and one of the other two.
Okay.
So we are 4 in number.
Okay. Perfect.
So I have picked like the gay biomechanics while pregnancy.
Okay.
That seems really interesting.
Yeah.
And there are like few research papers and stuff like that. It's going to be very similar to what you taught us, but it's going to be like a comparative analysis during the pregnancy.
Sure. Yeah.
Yeah.
No, it sounds really
so the thing is, like, what sort of calculation are you actually expecting from us?
Mm-hmm.
Like in the research papers, what I see, they usually have like a template. They did a software or did like data analysis. They don't have any breakdown calculation.
Yeah.
Like a book chapter.
Right.
So if we follow those, we won't be able to show you like any hands-on calculation.
Right.
Like very, very, very detailed calculation.
Right. So I'm expecting kind of something like this. And so, for gate biomechanics, it's naturally a dynamic process.
Mm-hmm.
And so you wouldn't be able to do any kind of static analysis unless you're going to do like any kind of like balance in terms of their stance, in terms of That I think would be good for statics. But for the dynamics, I would expect kind of a breakdown, kind of like this. And so maybe from the papers, you might be able to get some measurements in terms of like the joint angles with respect to time. Then you can plug them into here. Set up the equation for it first, plug them in here, and then show me some data in terms of what kinds of muscle forces are going on during a pregnant person's gait. So
like most of the papers, they have like a comparative analysis during the 3 trimesters.
Yeah.
The first, second, and the last one.
Sure.
Like how the physical changes occur in a woman.
Sure.
And stuff like that. So you want us to use those data?
Yes.
On this calculation, basically.
Exactly.
So what's going to be very helpful to us, like which book do you actually follow for the gate biomechanics?
So it should be the second book. So I always forget the title, but the Scott Dell.
Oh, the Scott one? Yeah. Does it have a chapter on gate biomechanics?
It does. Yeah. So it goes.
So you can have a look at that.
Of course. Yeah. So that's the second textbook, the one that we've kind of been focusing on since the first midterm. And so that was going to have that chapter on gate biomechanics is a lot more detailed than what we covered in class.
Yeah.
And so that'll be helpful. And I think they'll have probably some good references in there too, because I think the author of that actually is an expert at gate biomechanics too.
So basically, from the project, what you want is like both a quantitative and qualitative outcome.
Yes.
For the qualitative one, we can like come up with like some discussion that this sort of anatomical changes occur in women, so you must be very careful. You must be taking care of this.
Yes. Yes. So both components should be.
Okay. So we haven't finalized the topic yet. It wasn't just in my mind.
Sure.
They're thinking of something like sport biomechanics.
That'll work too.
Everything was just in the air. But my point of view was just as long as we can find something.
Okay.
Yeah, I think both will work. I think sports is a very rich area. And so I always have multiple groups doing different sports every year. So, but someone has taken soccer, and so that's the only one that we can't have at the moment. So, but yeah, that's possible too.
Like, do you mind showing us one of your best projects from the previous years, like as a guideline?
Yeah. I'll post it on Canvas.
Yeah, that's gonna be very helpful.
Yeah.
Like we can think what we're actually expecting from us.
Yeah. I'll post one.
Like Canvas. 1 or 2.
Yeah.
Do you have anything else?
Well, I'm gonna go to your office. Any help with the homework?
Okay, sure. Yeah.
Thank you.
Yeah, no problem. I know, it's so dark. Be careful getting home.
You too, take care.
All right, Cole, any final questions before I wrap it up? All right, see you next time.